All right. Good morning, everybody. Let's start here a new week for a new chance to get better. Okay. I hope you had a good weekend, got some rest, and prepared well for this week. So let's start here with some important announcements. Okay. For this week, you have two homeworks that are due on Thursday. The first one is for chapter 4, part 3, and then chapter 5. Chapter 4, part 3 is very short. Chapter 5 is a little bit long. Let me know if you need more time. Don't let uh, don't wait for the last minute to let me know if you need more time. I can always extend 1 or 2 days the deadline. For this week, we will have in-class assignment this coming Friday. There are no classes on Wednesday. I think it's a state holiday, if I'm not wrong. And also no lab this week. Okay, so we will meet today, tomorrow for discussion, and then Friday for the in-class assignment. Okay, let's pick up where we left on Friday. So we need to tackle this second example that we did not have time to finish on Friday. So let's recap here really quick. Calcium carbonate decomposes at high temperatures, producing calcium oxide and carbon dioxide. If 2 grams of calcium carbonate is burned and all the carbon dioxide is collected in a 1-liter flask at 25 degrees, what is the pressure of the gas? We are going to assume here that CO2 behaves as an ideal gas. The exercise provided the universal gas constant and also the molar mass for calcium carbonate. Okay, so let's set up this problem. So let me switch to my other screen here really quick. Okay, excellent. Okay, so first thing here, when we have a chemical reaction that produces a gas as a product, is to write the reaction. And that's the core of solving correctly this kind of exercise. So we have here calcium carbonate, a salt, that's going to be heat up. So again, if you want, you can indicate the heating up process using the triangle over the arrow. And the products that are going to be generated are calcium oxide, which is a solid, and CO2, which is a gas. Very simple reaction. All the stoichiometric coefficients are 1. So we have a direct relationship in moles, okay? Remember that the chemical reaction shows you the proportion in moles. So let's correlate the reagent with CO2 because CO2 is the gas product and it is the product that we are interested. From the reaction, we know that 1 mole of calcium carbonate produces 1 mole of CO2. However, what the exercise provided us is the mass of calcium carbonate. So you may go in 2 different ways to solve this problem. One way is to determine how many moles is equivalent to 2 grams, and then you have the direct relationship between moles of calcium carbonate and CO2. That's perfect, fine is one way to do it. And another way is to replace mole by the molar mass of calcium carbonate. Therefore, 1 times 100.09 grams of calcium carbonate produces 1 mole of CO2. Okay, so what I did here was to use the correlation that the molar mass is the mass of 1 mole of the compound and replaced mole by the molar mass. And the number 1 here comes from the stoichiometric coefficient of the equation. So we have to carry over to the setup. So with that, now I can write the proportion. First column is calcium carbonate, 1 times 100.09 grams, produces 1 mole of CO2. The second line, we are going to use the information that was provided during the exercise, 2 grams, and that's going to produce X mole of CO2. Cross multiplication, we are going to end up that the number of moles of CO2 produced is 0.020 mole. Okay, so from 2 grams of calcium carbonate, we are going to produce 0.020 mole of CO2 gas. We are going to direct all the gas produced to be collected in a 1 liter flask, and we are going to keep the temperature at 25 degrees. So what we are doing here is starting the reaction in some sort of a chamber. So initially we have calcium carbonate. Heating up the calcium carbonate will produce CO2 gas that's going to be directed to the collecting flask over here at the top. And we know that the volume of the flask is 1 liter. Temperature is 25 degrees. And we know that the number of moles of CO2 that we have trapped here is 0.020 mole. Of course, the molecules of the gas are moving in a random way. Eventually, they will collide with the walls of the flask, and that will create pressure. And that is what we are looking for. First thing before starting anything is to look at the universal gas constant, more specifically to the units of the constant, just to make sure we have everything squared up. Volume in liter, so we are good here. Number of moles in mole. The pressure will come in atmospheres. And attention here, the temperature always in Kelvin. Conversion between degrees Celsius to Kelvin, add 273. Therefore, we are going to have 298 Kelvin. Now that we know almost everything, we are going to simply use the ideal gas equation. This is the equation that will correlate pressure, volume, and temperature for an ideal gas. We are looking for the pressure. Volume is 1, number of moles 0.020. Universal gas constant is 0.0821, and temperature in Kelvin 298. Therefore, the pressure that the gas creates in this flask at those conditions is, according to my numbers here, 0.50 atmospheres, ATM. And that is the final answer. Okay, so let's move on. Okay, so next topic that I want to cover with you is regarding the Dalton's law. So I have to show this topic because it's in the sequence of the book. The Dalton's law will talk about mixtures of two or more different gases. So the classic example here is when we have two different gases in two compartments. So for this example, we have the red gas on the left side and a gray gas on the right side. Each of those gases, they have different pressure, volume, and temperature. Pressure, volume, and temperature. And when we open the stopcock right in the middle, the gases will mix up until they reach the equilibrium. And the final state, you are going to consider the mixture as a whole. And for this mixture, we have pressure, volume, and final temperature. The Dalton law will allow us to calculate the pressure, volume, and temperature of the final state as a sum of the individual pressure, volume, and temperature. So in the equation, what we have here is that the product pressure, volume, and temperature of the mixture is just a sum of the pressure, volume, and temperature of the gas A plus the gas B. And if you have more gases, you keep adding up, okay, until the N component. The example, we just have two gases, so you would stop the equation at this point. Okay. I'm not going to go in a lot of details here because we are not going to explore too much mixture of gases. And therefore, we don't need to talk too much about molar fraction and partial pressure because that's not going to be explored as well. Okay, so again, we will not explore the Dalton's law in a lot of details here. I just want to show you that when we have mixtures, we just add up the individual PV over T. Okay, so let me switch screens. All right, so now let's talk about diffusion and effusion of gases. Two different processes that are kind of similar, but each one has a very specific characteristic. Let's start talking about diffusion. Diffusion is the gradual dispersion of one substance through another substance. So again, here we have two flasks, one with hydrogen, another one with oxygen at different pressures. When we open the stopcock here, one gas is going to disperse in another gas. Therefore, that's the main characteristic of diffusion. When one gas disperses into another gas until they reach the equilibrium. So when you open a flask of perfume, for example, the molecules of the perfume will diffuse into the molecules of the air, okay? So therefore, diffusion, we have one gas being dispersed in another gas. However, for effusion, it's a very similar process, but there are two details. First one is that the gas will escape throughout a small hole into a vacuum, okay? So that is the biggest difference between effusion and diffusion. Effusion, we are starting with one gas and vacuum on the other side. And then the gas will pass through this small hole and fill up the vacuum. And therefore, diffusion is what explains why a balloon filled with a gas gets decreases the volume as a function of the time. When you fill up the balloon with gas, of course, the walls of the balloon are not perfect, and there are small holes into the walls that the gas, as a function of the time, will start escaping from inside to the outside. Therefore, they are diffusing from the balloon to the air. And as a result, the volume of the balloon decreases with time. If we fill up two balloons, one with nitrogen and one with helium, the balloon with helium will get smaller faster, And the reason for that, and we are going to see in some weeks, is that helium is a smaller molecule than N2 gas. If it is smaller, it is easier to escape when we have helium from the balloon to the air outside. And that's why helium balloons, they shrink faster than nitrogen balloons. Okay, very good. Okay, so now let's talk about the kinetic model of gases. So the kinetic model of gases was created in order to explain and understand the properties of basically any ideal gas. We already tackled some of the assumptions of the kinetical model of gases, but let's go over uh, all the points and then let's understand this kind of model. So the first hypothesis here is that a gas consists of a collection of molecules in continuous and random motion. Remember that the gas state does not have its own volume. Therefore, the molecules are going to fill up the space that's available to them. And molecules in the gas state, they are moving in a continuous random motion. Assumption number two is that the gas molecules are infinitesimally small points. Remember that the ideal gas, the molecules are considered so small that they don't have their own volume. Third hypothesis is that the molecules in the gas state, they move in a straight line until they collide, okay? So always movement in a straight line until they collide, and they will be kind of reflected by the collision and start moving in another direction. And all the collisions between the gas molecules and the walls of the flask are considered elastic. In other words, there is no energy loss when they collide with the walls, which will reflect in a constant speed that the molecules are moving. And fifth point is that the molecules do not influence in one another except during collisions. What this hypothesis is telling us is that there is no interaction due to intermolecular forces between the molecules of the gas. Okay, so they cannot attract themselves due to intermolecular interactions. They are all only influenced by the collisions between the molecules and the walls of the flask. Using the kinetic model of gases, we are not going to go into too many details how to get this equation. We just have to understand how the parameters here affect the speed. But the average speed of an ideal gas can be calculated as the root square of 3 times the ideal gas constant, R, times the temperature of the gas in Kelvin divided by the molar mass of the gas. So let's just note all the parameters in the equation here. Okay, so VRMS is the average speed of the gas molecules. R is the universal gas constant. T here comes from temperature. And we are always going to use it in Kelvin divided by the molar mass. What I want you to correlate here is the effect of temperature in the speed and also the effect of molar mass in the speed. Let's start with molar mass. If we increase the molar mass of the gas, that translates in a heavier gas. If the gas is heavier, the direct consequence in the speed is a decrease in the speed of the gas. So imagine here we have a truck not loaded with anything, and we are going to compare the speed of this truck with a truck loaded with dirt. Of course, the truck that is lighter will have a higher speed compared with the truck that is heavier. Therefore, a decrease in the molar mass of the gas will result in an increase in the speed of the gas. Okay, they are inversely proportional. Now, let's take a look regarding the effect of temperature on the speed of the gas. More temperature you provide to a gas translates in more energy for the gas to move around. So higher temperature will result in a higher speed for the gas. Therefore, they are directly proportional. Okay, so we are not going to calculate here the average speed for any gas, but we have to understand the effect of the molar mass and temperature on the average speed of the gas molecules. Okay, so let's move on. Okay, so that's the kind of thing that we need to understand and rationalize why we are observing this behavior. Let's take five different gases. The first one is carbon dioxide. Second one is oxygen. Third one is nitrogen, water, and finally hydrogen. And the idea here is to rank the average speed for each of those gases, considering that the temperature is all the same for all the gases. So remember that an increase in the molar mass will result in a decrease of the average speed of the gas. So we have here the molar masses. The heavier gas in this sequence is CO2, and that results in the lowest speed for this gas, considering that the temperature is the same. Now let's analyze the opposite in the ranking. So let's see who is the faster gas. So the fastest, sorry, who is the fastest gas? The fastest gas is going to be the lightest gas, or the one that has the lowest molar mass. And that's going to be hydrogen. And then to rank what is in between CO2 and hydrogen, then just look at the molar mass. Okay, so after hydrogen, water is has the lowest molar mass, and that's going to be followed by nitrogen, 28, and then oxygen, 32. And that's how you would rank the speeds of different gases using the molar mass. Okay, so this idea that gases with different molar masses move at different speeds is the principle used to enrich uranium. So the enrichment process of uranium means to increase the concentration of uranium-235. Uranium-235 is radioactive and is the one that's useful to produce energy or to produce bombs. While the other isotope, uranium-238, is basically waste. Okay, so non-radioactive cannot be used to produce energy or neither bombs. However, for some reason in the nature, this 238 has the highest percentage and 235 has the one of the lowest isotope percentages. The enrichment process is a process used to get rid of uranium-238 and increase the concentration of uranium-235. We cannot achieve 100%, but you can increase up to about 15% of uranium-235, and that's more than enough to produce energy or bombs in an efficient way. So if you look here, uranium-235 has a mass of 235 atomic mass units, and 238 has a mass of 238 atomic mass units. So that means this is heavy and this is oops, 235 is considered light. See that the difference is just 3 units of mass, but that will produce a difference in the speed which they move across a line, for example. So uranium-235 has a higher speed than uranium-238. Therefore, the enrichment process consists in move the two isotopes of uranium throughout a line and take advantage that the uranium-238 will move faster and will hit the ending first than the 238. Because the mass difference is so small, this process is really hard to achieve and also really expensive. And that's why we cannot get 100% of uranium-235. It's cost prohibitive. Okay? And that's how the enrichment process of uranium works. It's based solely on the different speeds that the gas moves around a straight line. Okay, and to finish up for today, now let's finally talk about the real gas. So before that, let's remember what an ideal gas is. In an ideal gas, the volume of the gas molecules is really small compared with the volume of the flask. Therefore, we will consider the gas molecules as a very small points. And also, there is no interaction between the gas molecules. The conditions that the real gas behave as an ideal gas, remember, is low pressure and high temperatures. We need to have low pressure because when you compress the gas, when you are pressurizing the gas, you are forcing the molecules to get closer to each other, and that will increase the probability of intermolecular interaction. Low pressure, we usually have the molecules so far apart that the interaction is basically, there is no interaction. And high temperatures will make the gas move faster. Therefore, when eventually each molecule gets close together, because the speed is so high, there is no time to get interaction, okay? So they will move in straight lines. However, when we have the real gas, we are going to consider that there are intermolecular interactions between the gas molecules, and also the volume of the molecules are taken into account. The equation that's going to describe the behavior of a real gas and correlate pressure, volume, and temperature is called van der Waals equation. And I'm showing here the equation in this slide. We are slightly similar to the ideal gas equation. The term on the right side is still the same, but if you look to pressure and volumes on the left side, we have two new factors that will correct pressure and also correct for the volume of the gas. Okay, so let's start talking about pressure. Pressure is going to be corrected by this factor A. A is a constant that depends on the nature of the gas, and we can find those in a table. So for example, here, the factor A for ammonia is 4.22.5, for example, and for hydrogen is 0.2476. Okay, so A is going to correct for the pressure, for the interaction between the molecules. And a second factor that's going to be used in the van der Waals equation to correct for the volume of the molecules that now needs to be taken into account is the factor B, is a constant B. And again, B depends on the nature of the gas, and we can find those constants in a table as well. So let's look here for ammonia, for example, is 3.707. And if we look for hydrogen, for example, is 2.661. A corrects for the pressure and is directly correlated with the ability of the gas molecules to interact with each other. B corrects for the volume, and it is intimately related to the size of the gas. Okay, larger the gas molecule, larger the B parameter will be. The real gas equation can be used in any situation of pressure and temperature and will provide the most correct description of any gas. While the ideal gas is very precise if we are using low pressure and high temperatures as the conditions. On the right side of the equation, we have the same thing that we had for the ideal gas, and number of moles are the universal gas constant, and T for temperature. And here, all the observations that were made for the ideal gas are valid for the real gas. Look at the universal gas constant units to determine all the other units that you're going to use in the equation. Okay, so now that I showed you the van der Waals equation to describe the real gas behavior, I think this is a good point for us to stop for today. We are not having lecture on Wednesday, and on Friday we will meet for the in-class assignment, okay? So I hope you have a good week, and I will see you on Friday. Bye-bye.